Hey guys, welcome to our first real foray into the world of integrals. Um, so the first few slides here are really just kind of descriptive. Um, this is kind of the big question: find the area underneath a given curve for some given interval, and that's what definite integrals do. And we're going to see how we derive them here real quick. We learned already how to do like left hand sums and right hand rectangular sums. You can see that if for this curve, it's increasing. And if we do the left-hand sum, we get an estimate, which is for sure too small because you're missing all these spaces here. And if we do a right-hand estimate, we get a sum that's clearly too big because we have all these extra pieces here. So the good guess is that the actual sum was somewhere in between 18 point whatever and 29 point whatever. The question here is about what's the actual area under the curve. So one way we've maybe talked about a little bit how to figure out what the actual area is to make the rectangle smaller or to increase the number of rectangles or whatever you want to call it. So here we're doing a 6 rectangle sum for both, and we get two numbers. This number is a little bigger, this number is a little smaller, and you can see we're kind of narrowing in. Now here the answer is somewhere between 18.6 and 30, and here it's somewhere between 20.3 and 27.8. The actual area is going to be in between these two numbers. And let's say I use 20 rectangles. Now my range for the possible answer is a lot smaller, 22.8 to 25.1. So the actual area is somewhere in between these two numbers. Then if I do 100 rectangles, looks like this, and I get something 23.8-ish for the left side and 24.2 for the right side. So now there's only like a 0.5 difference. So the area underneath these is for sure going to be something like 24, almost exactly 24, it looks like. So we're going to find out what it is. And well, we're actually not going to find out today, but what if I want to know the exact area? Well, we think about what we did here. We went from 4 rectangles, 6 rectangles, 20 to 100. If you think about some concepts we've learned in calculus already, what I really want to do is I'm like, what if this number up here gets like super duper big, like infinitely large? And then if I do that, I feel like I might get something very close to the actual area here. It turns out if you can figure out how to make this number up here infinity, that is, add up an infinite number of rectangles, then what I end up with is the actual area. So basically, we think about a Riemann sum that looks like this. The sum from, what was I using here? I's? Yeah. From I equals 1. I'm not going to write it out up here yet, of the f of x's times the delta x's. But like I want this number up here to be infinity, but I can't really plug infinity into, like I can't actually do infinite rectangles. So here's what you do. You put an n up here and you take the limit as n approaches infinity of this expression. And this equals the exact area. Basically, I'm saying, how do I get infinitely many rectangles? Well, I go from I equals 1 to n, and I let n go to infinity. There's mathematical treatments for this, but this is what I want. And this is the limiting form of the Riemann sum is known as a definite integral. And there's this long S that we draw, which represents the definite integral. Trust me when I say you'll get used to drawing those. Mine look a little funky there. But this equals the integral of f of x. And when we use the integral symbol, this delta x sub I becomes a dx. And we're going to put limits on we put limits here at the bottom and the top of this integral symbol. And the bottom limit here is the left-hand edge of the interval, and the upper limit here is the right-hand edge of the interval. So for this particular f of x in this particular problem, I started at 1, so I put a 1 here, and I went to 4, so I put a 4 here. And this is what this limit equals. It equals the integral from 1 to 4 of f of x dx. And what I just said there is how you should say it. The integral from 1 to 4 of f of x dx. And what this represents geometrically is the area between the curve f of x and the x-axis from x equals 1 to x equals 4. These are like x equals and x equals. Don't forget that. And kind of the way to remember that, like that it's x's, is because this tells you what the variables here and here are. That dx tells you that these limits are x limits. So this is from x equals 1. It's not from y equals 2 to y equals 17 or whatever this is. It's x equals 1 to x equals 4. So this is the exact area. It's called the definite integral. And it's like, to a large extent, the point of doing calculus is to figure out what the values of these things are. So the definite integral of a function is yeah, so this is the definition. I'm basically just going to write the same thing that I wrote before. Oh, just say I equals 1. So the definite integral of a function is the limit as n approaches infinity of the Riemann sum for that function, that interval. And again, this equals the integral from a to b of f of x dx. This is a more general representation with the a and the b, because it's like f could be any function, a and b could be any endpoints. It's always the left on the bottom and the right on the top. So just some kind of terms. The function here, the function f of x is called the integrand. The function inside the integral is called the integrand. The a and b are called a is called the lower, and b is called the upper limit, respectively. Lower limit, upper limit, integrand. This dx here is called the differential. And it's like, remember, this came from the delta x, but as like when we do this n approaches infinity, you can think about real quick, just to run back for a second, like the width of these intervals, each one of these is one long, or not one, because it's sometimes three. So each one of these, the width of each one of these is 3/4. There's 3 units, and I divided into 4 pieces, so that's 3/4. Here, each one is 1/2 of a unit long. Here, each one is 3/20ths of a unit long. Here, each unit is 3/100ths. So you can see that the delta x is getting smaller and smaller and smaller, which makes sense. These rectangles are very thin compared to these ones and these ones and these ones. So what's happening here, and the reason that we changed this to call it a differential, because this is like an infinitely small quantity at this point. So it's called a differential. It always has to be there. You can never have the integral from like 1 to 4 of 1 plus x squared. Like there's something missing here. And there's got to be a d something. It's not always going to be dx, but it'll often be dx. And it kind of makes it easier. You don't have to worry about parentheses with this thing, because whatever is between the integral and the differential is the thing you're taking the integral of. And we'll do more of this taking the integral later. Today, we're mostly going to talk about geometry as far as this is concerned, because remember that this integral represents the area between the curve and the x-axis. And so we're going to use geometry to do this. So this is just a note. Definite integrals are always the limits of Riemann sums. And when we actually do these, if someone did this in real life, you set up the Riemann sum and you take the integral after, and you take the limit afterwards. If f of x is continuous or continuous with only a certain number of jump discontinuities, then we say that f of x is, I've never known how to pronounce this word, integrable. You can take the integral of it, is what that means. This is like this corresponds to the word differentiable for derivatives. Differentiable means you can take the derivative. Integrable or that word means you can take the integral. And that's if any continuous function, you can take the integral of. It doesn't have to be differentiable, take the integral of it. So yeah, so this happens, I don't know if all the time, but it happens regularly in calculus and AP Cal, where sometimes they give you a function and the easiest way to take the integral is just to think about the area. And since we know a little bit about geometry, we can sometimes just use geometry instead of having to use integrals. And since you don't know how to take integrals yet, specifically, we're going to talk about it with geometry. There's not a ton left here once we get to the geometry stuff. So I'll break this here and we'll talk about this in the next one. Bye.